Cool. So Henry and I will be presenting on building and building on bulletproofs. So as you might guess, there's sort of two parts to this.
So in part one, it's going to be building, and what that means is like all of the pieces that we put into making the implementation that we did. So I'm going to tell you about the group we used, which is Ristretto and the Ristretto 255 group. I'll mention some details about parallel elliptic curve arithmetic, and also about Merlin transcripts for zero-knowledge proofs, and how these pieces fit together. And then I'm going to hand it over to Cathie, who's going to tell you part two.
Which is, once we implemented bulletproofs, what did we build on top of it? And so I'll tell you a little bit about our constraint system proofs and then our confidential assets protocol that we built over that. And the zero-knowledge smart contract language that we're working on currently that utilizes the constraint system proofs and Cloak. And then on top of that, how we can aggregate proofs to have smaller proof size and faster verification. Cool.
Okay. So for part one, I'm going to tell you about the pieces that we put into building this. The first piece is Ristretto. So before I talk about that, I'll tell you a little bit about the problem that we're trying to solve. And the problem is many protocols that you might want to implement would require using some prime order group. So in a paper, you'll see a sentence like this: let G denote a cyclic group of prime order P. This is from the Bulletproofs paper. And as an implementer, you're supposed to have one ready that you can use to instantiate the protocol. But how do you actually implement that? Probably you want to use an elliptic curve, but what kind of elliptic curve would you want to use? You could use a Weierstrass curve like SEC-P256K1, which is used in Bitcoin, or you could use an Edwards curve, such as curve 25519 or 4Q. And the big advantage of using a Weierstrass curve is that the curve itself gives you, the prime order group, which is the abstraction that you want, but there's a couple of downsides. So Edwards curves have faster formulas. Those formulas are also complete, so there's no special cases that you have to deal with, and it's pretty easy to implement them in constant time. So those are all pretty big implementation advantages. So you might ask, what's the problem that we don't actually have a prime order group, but there's this small cofactor? What's wrong with that? So what's wrong with it is that the security proofs for the abstract protocol don't then apply to your implementation. That could be bad. Having full validation that some input point lies in the prime order subgroup requires multiplying by that order, which is quite expensive. It'll negate most of the speed up that you'd get. You could try making some ad hoc tweaks to your protocol, like multiplying by a cofactor in an appropriate place. But if you have a complicated protocol, how do you know what's the right place? And you also then have to figure out are there going to be any subtle effects on my protocol? The answer is probably yes. So for instance, ED 25519 has different behavior between single and batch verification. So two conformant implementations actually are freely allowed to disagree on what signatures are valid, which could be a problem for some kind of blockchain. Another nice example is onion service addresses in Tor had to add extra validation because otherwise they would have accidentally ended up with 8 addresses for the same server, which is probably a kind of subtle and bad UX property. And then last year, most seriously, Monero had a problem where, due to insufficient validation, having cofactor 8 mean you could spend actually 8 times. So that's also unfortunate. So the lesson here is that Edwards curves are simpler at the level of the curve, but they push all of that complexity upwards into the protocol. So if you're a curve designer, that's great, because you can say, hey, look at my thing, it's so simple, but all of the complexity is not your problem. So there's a nice way to fix this mismatch, which is decaf and Ristretto. So decaf is a construction by Mike Hamburg that lets you construct a prime order group out of a non-prime order curve pretty efficiently. And Ristretto is a variant of decaf that works with cofactor 8 curves like curve 25519. So there's concrete parameters. The Ristretto 255 group gives you a prime order group. It gives you canonical encoding. It gives you a decoding that rejects any non-canonically encoded inputs. It gives you hash to group built in. You can use curve 25519 internally, so it's pretty easy to extend an existing implementation. But because of a really magical way that it's constructed, an implementation can actually swap out curve to 5509 for a faster curve internally with no problems with wire compatibility. And there's now an internet draft of a spec for it, so that's cool. So hopefully that sounds pretty good. But this actually allows you to do one more really cool thing, which is that because you're using an Edwards curve internally, you can actually implement the elliptic curve operations using parallel formulas. So there were these, the fastest formulas for doing elliptic curve operations were published in 2008. And the paper that mentions describes them mentions this scenario where you could have 4 processors executing in parallel. And that's pretty impractical to implement. So as far as I know, nobody did. But if you look more closely at these formulas, so I've drawn a diagram of them, the expensive steps of the formulas are all uniform. And so by tweaking them, you can actually do a SIMD implementation, which is pretty fast. So here, these orange bars are the SIMD implementation that I wrote. One backend uses AVX2, and the other uses IFMA. And so the IFMA implementation is just barely slower than 4Q, even when using the patented endomorphism speedup. At the bottom 2 lines are libsec-p, with and without using endomorphisms. So depending how you compare, at the end of the day, you get like a prime order group that's up to 4 times faster, and not using any assembly or anything. It's all written in Rust. So that's nice. And then the other piece that went into the implementation that I want to tell you about is these Merlin transcripts. So there's this thing you might have heard of called the Fiat-Shamir heuristic, and basically the idea is that if you have an argument where there's a prover and a verifier, and the verifier is sending random challenges to the prover, then as long as you believe in random oracles, then you can replace a verifier's random challenge with a hash of the prover's message. So that sounds like a pretty simple idea, but again, there's a lot of weird complications if you might try to do this in practice. So you might forget to feed data into the hash if you're just building up this big thing and then hashing it. You have to worry about how exactly are you structuring the data that you put into the hash. If you have a multi-round protocol, then you have to take some challenge output and you have to figure out a way to construct that and stick it into the hash of the next round and make sure that everything's bound together. If you want to have domain separators so that different applications have proofs that aren't interchangeable, so that someone can't take a proof out of one part and stick it into another part, you have to have a way to do that. So there's a lot of edge cases. So another thing that you could imagine is you could just have a transcript. And then in the paper, when it says a prover sends L and R to the verifier, you could just write transcript commit L, commit R. And then if you wanted a challenge scaler, you could just write that. And then that way, the implementation matches the paper, and it's a lot easier to know what's going on. So that's what Merlin does. It's a construction built on Strobe, also by Mike Hamburg. And what it does is it allows you to implement your protocol as if it were interactive, passing this transcript parameter through all of your proving and verification functions. So the Fiat-Shamir transform is done in software, not by hand, so it's harder to miss things. It does automatic message framing, so you don't have any problems with ambiguous encodings. Very easy to do domain separation, because when you build one of these transcripts, you have to give a label, and if you want to do something more complicated, you can just commit arbitrary structured data into the transcript. And it also lets you do sequential composition of proofs by sticking in a domain separator and then running 2 proving functions on the same transcript. So that's pretty cool. And hopefully that sounds like a fun thing. But there's one more thing that this lets you do. And in order to tell you about that, I'll give you a little context on bad entropy for Schnorr signatures. So in Schnorr signatures, you have a signer, which is kind of like a prover. And at some point, they have to generate a nonce, which is used as a blinding factor. And if they leak the blinding factor, that's really bad for them, because that's their secret key is recoverable. Also, if they ever reuse one, that's also bad. Sony had that problem with the PlayStation keys. And even if they just leak a few bits of blinding over a lot of different signatures, that's also pretty bad. So this class of attacks on having bad entropy probably also applies to all these zero-knowledge proof systems that people are building. So it'd be cool to have a kind of defense in depth mechanism, and that's what you can do if you use this transcript. So you can provide a transcript-based RNG. So strobe is using catcheck internally, so you have a nice sponge function available. And whenever you want randomness, you can just clone the transcript state. So that means that all of your future output is going to be bound to all of the record of all the public data. Then you rekey the sponge with the prover's witness data, so that you have at least as much entropy as your secrets. And then you rekey with some external RNG input just to prevent some problems with deterministic signatures. So you can think of this as being like synthetic nonce generation, but generalized to some kind of arbitrary zero-knowledge proof protocol. And hopefully that would give you a nice defense in depth against that whole class of attacks. So when we put all those pieces together, our implementation's like pretty good and fast. So using this IFMA backend, our verification is 3 times faster than libsecp and 7 times faster than Monero. Using AVX2, the speed up drops to like 2 to 5, and it's even when we just use the serial implementation, it's also still faster. And we actually get a bigger speed up on proving, but that's not as important for as verification. So that's part 1. Now it's part 2 with Cathie.
Cool. So after we have all those building blocks, implementing Bulletproofs was quite trivial. So then part 2, I'm going to talk about what we did once we actually implemented the Bulletproofs paper. So the first thing we did was we made a constraint system proof protocol over the paper. So I'll talk a little bit about what are constraint system proofs in the first place, like why do we care? And I'll walk through one example of how to use our API to build a constraint system proof. So a constraint system is a collection of 2 kinds of different constraints. We have multiplicative constraints, which basically say 1 secret times another secret equals a 3rd secret. And we have linear constraints, which is a linear combination of secrets with clear text weights. And you set that to be equal to 0. So these are our 2 kinds of constraints, and with them we can actually represent any efficiently verifiable program. So you can see how we can do any kind of computation, any kind of smart contract verification using a constraint system. And then a constraint system proof is simply a proof that all of the constraints in a constraint system are satisfied by certain secret inputs. So we implemented constraint systems, and then we made an extension to this protocol where we allowed for use of challenges. So Bulletproofs has this really nice property where you can actually make constraint systems with no setups, so you can build a constraint system on the fly. And what this allows us to do is to get and use random challenge scalars from commitments to variables. And this is actually using the transcript protocol that Henry talked about earlier, where you can make commitments to variables, put them into the transcript, and get random challenge scalars back from that. This allows us to make smaller and more efficient constraint systems. And I'll walk through one example of a constraint system that's actually way more compact because of these random challenge scalars. And this is currently under research. So a gadget is a term that we use for just a collection of constraints, and you can actually build multiple gadgets together into one constraint system and make one proof over it. So an example is a shuffle gadget, where you want to prove that the outputs of the shuffle gadget are a valid permutation of the inputs. So in this example, we just have 2 inputs and 2 outputs, and you want to prove that C and D equal A and B, or C and D equals B and A in this case. So we can do this many different ways, but actually using a random challenge scalar x, you can use equality of polynomials when roots are permuted in order to do this extremely efficiently. So a minus x times b minus x equals c minus x times d minus x for a randomly chosen x, if and only if c and d are a valid permutation of a and b. So that's pretty cool. So what we basically want to do is to represent this constraint using our constraint system API. So I'll walk you through how we do that using the API that we put in place. So here's our gadget code. The toShuffle function takes in a constraint system and 4 variables for A, B, C, and D. The first thing that we do is get a random challenge scalar x. So this should look familiar from the transcript earlier. This gives us our challenge scalar, and then we create a multiplication constraint where we pass in a minus x and b minus x, and then expect that the variable for the a minus x times b minus x is input mole. And then we say, again, c minus x times d minus x should be equal to output mole, and that's another variable. And then we add a linear constraint on line 12, cs.constraint, and we say input mole minus output mole equals 0, which basically is the same as saying input mole equals output mole. So when you put all these three constraints together, you get a minus x times b minus x should be equal to c minus x times d minus x. So that's pretty cool. That's actually it, and you can see the sample code, and it makes a valid constraint system. But we actually have to use this as a prover to make the proof and as a verifier to verify a proof. So let's walk through an example of that. In this case, the prover will make a new prover instance, which is actually an instantiation of the constraint system trait. And then it will take its plaintext scalars A, B, C, and D and commit them to the prover constraint system. It'll get back commitments and variables for each of those. And then it will pass the prover constraint system and the 4 variables into the toShuffle function, which is what we just saw on the last slide. This toShuffle function, as you remember, adds constraints over these variables in the constraint system such that these variables must satisfy the constraints that C and D are valid reordering of A and B. And then you create a proof just by calling .prove on the prover. So then the prover has this proof, it has these commitments to A, B, C, and D, and it passes these to the verifier. The verifier then makes its own constraint system. The verifier is an implementation of the constraint system trait, and then it commits these commitments to A, B, C, and D into the constraint system. This gives the verifier these variables. So the difference between the prover and the verifier is the verifier doesn't actually have access to the secret scalars, whereas the prover did, which is why the commit function looks different. But the verifier calls toShuffle in the exact same way. It passes these variables in over the verifier constraint system, and then it calls .verify on the proof. And as you can see, this allows both the prover and verifier to construct the exact same constraint system, and that allows you to successfully create and then verify a proof over that same constraint system. So you can actually see the full sample code for the toShuffle in our GitHub repo. So what I just went over was an API for making multiplicative and linear constraints, our protocol extension for making challenges over commitments to variables, and then I walked through a shuffle gadget example that uses the constraint API and uses the challenges to make an extremely efficient shuffle. So this toShuffle on its own doesn't actually do anything extremely useful, but if we put it together with a bunch of other gadgets, we can actually make a confidential assets protocol using these bulletproof constraint systems. So that's pretty cool. The gadgets that we have in this confidential assets protocol, which we call cloak, are shuffle, merge, split, and range. So shuffle, in this case it's a k-shuffle, proves that the outputs are a valid reordering of the inputs. Merge proves that the outputs are either a merge or a move of the inputs. Split is either a split or a move of the inputs. And the range is a check that the value is not negative. So that's similar to the range proof in the paper, except constructed using the constraint system API. So these are the building blocks that we have, and we put it together to make a confidential assets protocol like so. So as a reminder, a confidential assets protocol is one in which both the quantity and the asset type of all of the inputs and outputs are kept secret. And so as you can tell to an external observer, you actually can't tell what type or how many, what type or what the quantity of inputs and outputs are, but you can verify that it is a valid transaction, that the inputs correspond to the outputs. As a prover, however, you actually have to make the individual assets move between the shuffles, merges, and splits and range proofs. And so I'll walk through what the prover generates to show you how exactly this transaction works. So suppose you're a prover and you want to make a proof that your inputs, $5, 3 yuan, and $4 equals 3 yuan, $6, and $3. So first you want to prove that there's a random shuffle where you reorder the input values by asset type. So now we group the dollars together here. And then you want to merge all of the assets of the same type together. So $5 and $4 become $9, and this basically allows you to take the sum over each asset type. Then you shuffle again just to move the non-zero items to the top, and then you split each asset type into the target payment amounts. So $9 gets split into $6 and $3 because that's what we expect for the outputs. And then the last shuffle proves that our output ordering is a valid permutation of the input ordering to that shuffle. So $6, $3, and 3 yuan just get shuffled into the output ordering that we expect. And then the range proof shows that none of these outputs are negative, because if you have negative outputs, that's bad. You can create money out of nothing. So that's the whole walkthrough that the prover does. And then you make a proof that all of these values are valid inputs and outputs to each of the gadgets. And you give that proof, and you give this gadget construction to a verifier. And to a verifier, all you see is a 3-in, 3-out cloak transaction, which is indistinguishable from all other 3-in, 3-out cloak transactions, and a proof. And you don't actually know how these values were moved and split, but you can tell that it's a valid transaction. So you can actually see the spec and code at this link here. There's a lot more details that I sort of glossed over. And also, this looks like a really complex protocol, but actually the majority of the cost of running this is in the range check, because the most expensive part is the multiplications, and the range check requires vastly more multiplications than the shuffles, merges, and splits. And so this is not actually that much more expensive than doing a simple confidential transaction proof, which you'd have to do a range check for anyways. So that's a cool side note. Cool, so we created this cloak confidential assets protocol, and then we're like, well, it would be really great if we could make more flexible contracts than just a proof of a confidential asset transaction. So what we're working on now is ZKVM, which is a zero-knowledge smart contract language. So if you were here at this conference last year, I actually presented on TXVM, which is what we were working on at the time, which is a smart contract language. And TXVM aimed to have deterministic results, an expressive language, and a safe execution environment. And ZKVM, which we call the zero-knowledge virtual machine, takes a lot of concepts from TXVM and then adds confidentiality to it. So I think that's pretty cool. And we do that by taking several concepts from TXVM, such as having values and contracts that are first-class types that have a guaranteed law of conservation. So you can't actually create or destroy value without satisfying very strict checks. Also, contracts implement an object capabilities pattern, and we have a deterministic transaction log, so you can deterministically reason about what effects your transaction will have. But with the addition of bulletproofs, we actually get an additional ability to operate on encrypted values and contract parameters, the ability to make custom contracts using the constraint system proof protocol that I showed earlier. And you can also protect asset flows with Cloak, which is also what I explained earlier. So we take all of these concepts and group them together into the development of this really awesome zero-knowledge smart contract language, which is currently under development. So you can follow along. We have an open source repo. So wait, it gets better. You can actually do aggregated proofs using bulletproofs, where an aggregated proof is smaller and faster to verify than the M individual proofs that it aggregates. So this is really awesome. The problem or the difficulty with aggregated proofs is that it requires a multi-party computation protocol with multiple parties and a dealer in order to create an aggregated proof. And this can actually be fairly complicated. When we implemented the aggregated range proof protocol, this was sort of the chart of different state changes and messages being passed back and forth. And it's like it's not trivial to keep track of all these state changes. And it's extremely important for safety that you do each state change both in order, and you make sure that you don't do one state change twice, or else you might leak secrets. So what we ended up using was session types, where we encoded the protocol states into the Rust type system. Because of the memory management model, you can actually make functions that consume the previous state for each prover or each party and dealer state, and then output the next state. And this actually statically ensures correct state transitions. So you eliminate the possibility of multiple evaluation attacks. So we implemented this for range proofs, and this is also possible to use this approach to do aggregated constraint system proof construction. So we wrote a little bit about that here, and this allows us to have even better performance than individual proofs on their own. So as a recap, Henry talked about all of the pieces that we built that can be used to make zero-knowledge proof systems that we used to build bulletproofs, and then we implemented bulletproofs, and then we built a bunch of things over bulletproofs, including a confidential assets protocol and a zero-knowledge contract language. So yeah, that's everything we wanted to present on. We have some further reading because I know this is like very dense and we glossed over a lot of details. The Bulletproofs paper, we also have a link for all of the interstellar work that's going on, including Cloak and the zero-knowledge virtual machine language. And then there's also information about the Ristretto group and the Dalek API and documentation. And I do want to give a shout out to Oleg. So Henry and I and Oleg worked together on a lot of this stuff, and he was super involved and actually worked on primarily, he was the main author of like the constraint system challenge extension and a lot of parts of ZKVM. So yeah, that's everything we had.
Very impressive. Again, we have time for questions. If anybody has any questions? Henry, come up on stage. So just to clarify, this is all open source?
Yeah.
Anyone can use it?
Yeah. And the pieces, I mean, are meant to be mostly reusable. So hopefully they will be used.
Can you say a few words about how is this going to get to, like, you guys are building all of this. What's your plan for deploying this to the world?
That's something that we're still talking about because we still don't have ZKVM like fully working. But the confidential assets protocol is pretty much like working and usable in its own library, and so we encourage anyone to use that. That is ready to be used.
And the language is generic enough that anyone who has like a need for any zero-knowledge statement that they need to prove, the system can actually adapt to actually do that, to do those proofs?
Actually, we designed the language, similar to TXVM, we designed the language specifically to work with transaction value flows. And so it is not with the goal of doing any potential proof of any statement ever, although you could do that with the constraint system proofs, but the language is designed to allow you to safely do proofs over values and in a way that restricts whether you can create or how you can create or destroy value. And so basically when we design the language, we prioritize safety and ability to reason about creation and destroying a value over flexibility. And so this is actually something that's designed specifically to do like financial transactions.
Awesome. Any other questions? We have some time. Yeah, please. Speak up.
Yes, I'd like to ask here fundamental question. Suppose there are aggregated MPC. So who are the players of the multi-party computation in the use case of smart contracts?
Maybe just repeat the question.
So the question is like, who are the players in the multi-party computation protocol? For the smart contract use case, I think probably the idea would be that since the proofs, you get like log compression on the proof size. If you have a bunch of people who all want to have a proof of their contract execution included into some block or something, you could imagine having some kind of like untrusted dealer service where people can just register, like if you want to submit a transaction, instead of submitting that directly to the chain, you would like phone up this aggregation service, and then it would group you together with other people who wanted to make transactions at the same time. And it could do stuff like, depending on like the rate of requests, it could adjust the aggregation size. And that way you could have a kind of like a pre-filtering or like pre-compression before you commit on-chain data.
Yeah, so I had a question. If I have the constraint system, if I already build a proof and put a lot of work in building a proof for a snark, a snark library, can I also use that then? Is it just plug and play, or how much work is it to change my snark proof system, my snark constraints into something for this library?
Yeah, So currently, there's no like ability to plug and play a snark that you've already built into a Bulletproofs constraint system, but we're actually talking to folks on a way to make a potentially shared common layer, whether that's a shared RNCS implementation, because I know like some snark implementations use like an RNCS to snark conversion, or a higher level language. We're not completely sure, but we would very much like to be interoperable with snarks in the longer run.
Yeah, so for your aggregation for multi-party computation protocols, the dealer is assumed to be centralized?
Yeah, there's actually multiple ways that you can do proof aggregation. As you can see in the paper, like Benedict outlines multiple ways. The way that we thought was sort of the most straightforward to implement was to have like a centralized dealer. I will note, though, that you don't have to trust the dealer to not leak your secrets, because the dealer never gets access to the secrets. The dealer only gets your commitments, and the only thing you have to trust the dealer to do is not go offline, but the worst case that happens is then you don't get an aggregated proof if they go offline.
Awesome. All right. Thank you very much. Let's thank the speakers one more time.